Today we're going to have a great talk by Shoko Sakai, who is a researcher in the UCLA Galactic Center group. She did her PhD at Dartmouth, and she actually did her postdoc here at Caltech when she was working on extragalactic scales. But she's been working mostly lately in the Galactic Center group, looking at Sagittarius A star, the black hole in the center of our Milky Way galaxy, and using it as a laboratory to understand physics. So thank you.
Thank you. All right, thank you. So as Katie said, so I have not been actually working in the Galactic Center group for that long, only for a few years. So I'm relatively new to this field, but I hope that I'll be able to tell you the story of what Galactic Center group has been doing at UCLA for the last 25 years to study the supermassive black hole at the center of our Milky Way galaxy. And hopefully, you know, I mean, like last few years for me has been like going back to grad school and learning all these new things every day, and it's been kind of fantastic experience for me. So hopefully I can convey some of that to you this morning. So, okay, let's see. So obviously the work I'm presenting today is not all my work, and it's really a combination of 25 years of research done by, here's Andrea right here in the middle, and Mark Morris and Eric Becklin. Those three started the Galactic Center group research 25 years ago, and really the collaboration of many, many, many postdocs and researchers and graduate students over a few decades. Let's see. So here's a brief outline of my talk. I would like to start, or let's just start this talk with a very simple question of, do supermassive black holes exist? Then I'd like to discuss some properties of the Milky Way galaxy black hole. And if I have time, I'm not sure if I have time to do this, just beyond mass and distance to the black hole, maybe I can discuss a little bit about the environment of the black hole. Then I would like to talk about the experiment that we were fortunate to conduct about a year ago during summer of 2018 to measure the gravitational redshift around the potential well of the supermassive black hole about a year ago. Then I will conclude with what's coming up in the future, near future. So let's see. So do supermassive black holes exist? And I think most of you know the answer to this question. Otherwise, you probably wouldn't be sitting here. We do know that. And then the other thing is that Kelly's talk indicated that we do know that most galaxies do, that we see supermassive black holes in just about every galaxy that we observe. And so the consensus is that the black hole is found in the centers of most galaxies, including our own Milky Way galaxy. So what Andrea Getz was interested in some 25 years ago was to find this supermassive black hole at the center of our own galaxies, not any galaxy, but the center of our galaxy. By monitoring stars, the way she wanted to do this was to monitor stars around this black hole. So can we actually see the stars move around the black hole? So this will be the most direct way of measuring the mass of the black hole. But in order to do that, if you think about what needs to be done, if you want to actually observe stars moving around the black hole some distance away, now this is at the center of Milky Way, it's only 8 kiloparsecs away, or 26,000 light years away, which is very short distance compared to all this like the extragalactic supermassive black holes that we've been talking about, but it is still pretty far away. The only way to see this dramatic gravitational effect is to measure something in a very small region, okay, very far away, and so on. Okay. And then so in order to do that, some technological advances had to be made first to give this unprecedented spatial resolution in order for this experiment to succeed. So let me just start with the two observational goals here. The first is that we want to observe as many stars as possible to find the most interesting ones, which means we cannot just observe the brightest candidates in the galactic center of our Milky Way galaxy. So we need to go fainter. Okay, so we need to probe as many stars as possible around the central potential of the Milky Way galaxy. So we want to observe fainter stars. We want to observe as many stars as possible. And the second, as I said in the previous slide, is that the need for high resolution imaging. Okay? It would be nice if you could actually see a star orbiting around the black hole in your lifetime. Okay? In order to do that, you have to see a star very close to the black hole. Right? You don't want a star that's really far from the black hole that it's only going to move tiny little bit in 10 years, 20 years, or even 80 years in your lifetime. Okay? So you want to see some star very near the black hole. That means that you need extremely high resolution observation. Okay? Talking about like several thousand astronomical units. That's the kind of resolution that she was going after. Okay? So as I said, several advances had to be made in terms of technology. That is a telescope technology. The one is improved infrared detector sensitivities with larger format. So the infrared detector is basically technology. It's a military technology that was declassified, I believe, in the 70s or early 80s. And in Galactic Center Group, we used the near-infrared camera that is on Keck Telescope on Mauna Kea in Hawaii. Actually, the near-infrared camera was developed here at Caltech by Keith Matthews' group, and we've been using that instrument for a long time. But this basically revolutionized our ability to see, to observe Galactic Center, and then actually resolve individual stars at the Galactic Center. Another question, is that why infrared? Okay? Why not? Why don't you use Hubble's telescope? They seem to have a pretty good resolution and so on. You can see these tiny little things with Hubble Space Telescope. Well, we need to go to we need a wide infrared detector. So if you look at this picture, it becomes pretty obvious. This is a little bit misleading, but so this is the top one is the optical picture of the so the Milky Way galaxy. The Galactic Center is somewhere right at the center of this picture. Okay? And this has actually blown up a couple of times. So this Spitzer image, so Spitzer Science Center is right next door. So this picture is made right next door again. So this is a Spitzer telescope image, which basically is a tiny little part of this, the top optical view of the Milky Way galaxy. So if you look in with a visible light, you can see it's very dark. You cannot really see any stars there. Okay? So there's so much dust, the molecular clouds and so on, that obscures the light, basically blocks the light from reaching us. And then so you need to go to a longer wavelength to actually see anything in the galactic center. So this was the reason why we needed to wait for the infrared detector, a really good infrared detector to be available. The other thing is the resolution. As I say, you want to be able to observe individual stars very close to the central potential of the galaxy. So in order to, so there's a correlation basically, this is really astronomy 101 here, but there's a direct correlation between how large the telescope is and how small the resolution you can get, okay? Which is basically, this is lambda is the wavelength that you're observing with. In infrared, we usually observe a 2.2 micron. Diameter of Keck telescope is 10 meters. So you actually get about 40 milliarc-second resolution. Okay, this is pretty good. 40 milliarc-seconds on the 10-meter telescope. However, most of you who have actually done observing would know that, so at the distance to 8 kiloparsecs, that's the distance to galactic center, 40 milliarc-seconds corresponds to about 400 AU, which is great. That's exactly the scale, the resolution that we are looking for. However, you'll know if you actually observe a 10-meter telescope on Mauna Kea, you get about the seeing or the resolution about only like 10 times worse than this, 0.5 arc-seconds or so. Okay? And that is because of the atmosphere. The atmosphere blurs the image, the twinkle, twinkle, little star effect. Right? That is really, really awful for astronomers. So what do? So we are able to freeze the atmospheric distortion. Right? So the light source comes from some galaxy or star near the galactic center or anything, and that has to, unfortunately, it has to travel through the atmosphere right before it reaches the telescope, and it blurs, so the wavefront that's coming from the light source gets distorted. And that's where you get the twinkling effect. It makes the scene much worse, so the resolution of the picture that you're getting is much worse. And this is a very clever method. So what it does is in real time, this deformable mirror actually moves around several hundred times a second, and it corrects for this distorted wavefront in real time, and it gives us a sharper picture. Okay. So here is a quick video. Is it playing? Let me see. Aha. Okay, so this is clear, the picture of the galactic center with no adaptive optics. This is called adaptive optics. And then you can see with the adaptive this is with no adaptive optics, and you can look at the center region of the picture, and you can see much clearer picture of the region with the adaptive optics on. Okay, so in the same region here. So because of this, now we are really able to observe the region of galaxy with about 50, 60 milliarc seconds resolution consistently. So just wanted to mention that the UCLA group is not the only one that has been monitoring those stars around the galactic center, but there is a Germany group led by Professor Genzel they actually started this whole exercise earlier than the UCLA group. 1992, they first used the 3.6 meter telescope, and then moved on to very large telescope in Chile, the 8 meter telescope, and more recently, I'm sure some of you have read the news, but the interferometry, the 8 meter telescopes, has now given them 4 milliarc second in resolution and so on. Okay, so the two groups have been working on this for about 25 years at this point. But both of our groups, both work in infrared, about 2.2 micron wavelength range. Okay, another advantage of this adaptive optics is now it added the spectroscopic data, not just imaging. So at first, so 1995, the UCLA group has started this whole experiment with just taking pictures one year after year. Every summer, you go to Keck, and you take a picture of the same region. You go back and take another picture, and so on. And then with the adaptive optics in 2004 or 5, so it was now possible to actually take spectrum of each star. Here's just a couple examples. Basically, bracket gamma. This is the hydrogen line around the 2.16 micron wavelength. This line is used to measure basically the line of sight velocity through Doppler shift. Okay? And in astronomy, in physics, so like it just measures missing third dimension of this motion. That measures the line of sight velocity. But in astronomy, actually, the spectrum tells us a lot about astrophysical nature sources, those stars that we observe. And in fact, that's where we saw a lot of surprises. Hopefully, I have some time at the end to talk about this. But you can see with the spectrum, you can see some stars are actually old and some stars are young. And so when you can start dating those stars, the ages of those stars can be measured. Okay. So here is basically the bottom line of the over 2 decades of monitoring the stellar orbits in the galactic center region. So what you see is that there are actually, let me repeat this. Is it in the repeat? No. There are actually 3 stars for which we have complete orbital coverage, which is this one, and you can see this one, and then you have this one. But this actually plot what it's telling you, I'm going to freeze it right around there, is that you can see the dotted line, the dashed line, and some solid line. The solid line is where we have the spectroscopic data as well as the imaging data. So you see a lot of those ones. Some of the stars only have dashed lines, which means we have no spectral data yet. Okay? And so for this yellow one, which is called SO2, this is the most interesting star for us. It has the full orbital coverage of astrometric data, obviously the positions, as well as spectroscopic data. This one actually, so then this SO2 orbits around the supermassive black hole every 16 years. Okay, so that's just short enough and for us to be able to actually cover the entire orbit and then start thinking about interesting physics as well. Okay. So using this orbit of SO2, here's the orbit of SO2 covering about 25 years of data. So it actually wraps around 1.5 times around the orbit. We know this mass of the supermassive black hole at the center of our galaxy to be about 4 million solar masses, but plus or minus 0.2 right now. That's the best estimate right now. And I think this is probably the most solid case for the strongest case for the existence of supermassive black hole. Okay. And I forgot to say at the beginning, but among all the galaxies with supermassive black hole, the Milky Way Galactic Center is the only one that we can actually resolve stellar orbits. It's close enough. The next one is 100 times further away. And just it's not possible to look at individual stellar orbits, so that you have to rely on more indirect method of looking at the gas movements and so on around the black hole. But our galaxy, this supermassive black hole is the only one where you can actually see the individual stars, and that means we can actually study the environment surrounding the black hole as well. Okay. I said this already, so let me just repeat again. But so here is a diagram just showing the mass of these galaxies, of the half mass of the black hole mass, supermassive black hole mass, so all the galaxies, and the density. And then so this puts the galaxy, our Milky Way galaxy black hole, it sits right up here. Okay. So what this means is that at least we know directly, and probably very well, that at least one supermassive black hole, coming back to the very first question on the outline, do supermassive black holes exist? We know that at least one supermassive black hole definitely exists from a pretty direct method. And that's why we also believe, that's probably why we believe that others do too. There are other blacks, so there can't be, if we see one supermassive black hole, there have to be others as well, very likely at the centers of all those galaxies. Okay, and this diagram is not the greatest one. Again, coming back to the same idea that was presented in the last lecture, that one of the reasons that we are driven to study supermassive black holes is because of this correlation between the mass of the black hole and the mass of what's called a stellar bulge, which is basically the central part of those galaxies that you see. So there's a rough correlation between those two quantities. And then those two things occupy completely different sizes. The black holes are an astronomical unit scale, where the bulges are on the thousands of light years scale. Okay? So it has been, as said before, mentioned before, it's been intriguing us why this correlation even exists at all. Okay? How do they actually talk to each other? There's the black hole at the middle somehow has something to do with the evolution of galaxies. So this is another reason that's been driving us and lots of other astronomers to study black holes. So that brings us to the next part, or the next section of the talk, and that is, once we have this complete orbit SO2, that star that looked at with a yellow orbit on that figure on the plot is called, named SO2. Anyway, that brings us to the topic of the general relativity, and basically to be able to measure the gravitational redshift as the star reaches its closest point in its orbit near the supermassive black hole. And this actually took place back in 2000, a year ago, during summer 2018. Those are the 3 tests of GR tests. All 3 of them we hope to do. Who knows how long it'll take. The next test will be precession and periapse, and then the 3rd test will be maybe we'll be able to actually observe the spin of black hole using the supermassive black hole at the center of our own Milky Way galaxy. And I will touch base on these 2 towards the end of the talk. Okay. So in order to study or to measure this gravitational redshift effect as the star SO2 goes very near, this is the star actually, and the black hole is right around here, as it reaches the closest approach point in its orbit near the black hole. The one thing that the requirement was that we had to have the complete orbit. The simulations show when you don't have the complete orbit, there's a lot of biases that get thrown into it, and then you don't really get quite the right answer. So the fact that SO2 has a complete, not just the astrometric, but spectroscopic data as well for every point or the orbit. So that was like a perfect opportunity for us to be able to test the general relativity, the gravitational redshift. Okay, so there was a simulation done by one of the postdocs at UCLA that showed that those major events had to be basically observed. You have to, if anything, you don't have to observe anything else, but you have to observe those 3 times during 2018. One is astrometric, basically the closest point, right? It's an elliptical orbit around the supermassive black hole. When it gets to the closest point, that's one point we should really observe if we want to get to this experiment right. And remember, this experiment cannot be done. If we miss 2018, we had to wait 16 years. So luckily, it happened in May. And I say luckily because Keck Telescope's in north. And Sagittarius is a southern object. It's only visible in summer. So if this happened in December, we were not able to do this experiment whatsoever. So it's kind of out of luck that this happened smack in the middle of the best observing time of the Galactic Center from Keck Observatory. So that was the closest approach in May. And the other thing was that the spectroscopic data had to be taken when the velocity reaches the maximum point and the minimum point. So the orbital SO2, if this is a black hole, orbital SO2 comes in like this. It comes closer to us and it goes back. So it had to get, when it reaches the fastest speed, is as it comes towards us, and then the most negative speed as it goes away from us. That happened in September, right before as Sagittarius star was setting. So it turns out, this is just for fun, I just wanted to show the next few slides, but 2018 turned out to be one of the worst years weather-wise on Mauna Kea. If any of you observe on Mauna Kea, we were lucky to do this very first observation in March. This is a UCLA remote observing room. First observation 2018, hooray. And then nothing happened. Just rain, storm, snow, whatever you can think of. Mauna Kea was pretty much shut down for a long time. But we managed to get the maximum RV, the radial velocity data in late April, after a lot of bad weather. And if it's not bad weather, there's a volcanic eruption that we actually caught as we were observing on the cloud cam. And that ashes eventually reached us and we had to shut down. So it was one of those times. But we feel very lucky actually to be able to get all this data we did in 2018. So anyway, so we were able to get the minimum velocity data. I'm sorry, this is the closest approach. This is astrometric. So sorry, this is basically the distance from the supermassive black hole as a function of time. And as it reached the minimum approach area time, we were able to observe it. And then again, at the minimum velocity in September. Okay. So I'm not a GR expert, but this is what we tried to do. Basically, if you look at this equation, you can sort of ignore the very first term here. This is just the offset we have to apply because the radial velocities are observed using many different instruments, and in fact, many different telescopes as well. We use the Subaru telescope, Gemini, and so on. And each telescope has its quirkiness, and you have to just kind of add this offset to make all the velocity on the same consistent scale. And so that's just a term. But this RV, or the radial velocities, is the radial velocity you would observe if we were purely Keplerian orbit. And then the last two terms is basically the transverse special relativity term and the gravitational redshift term here. And this is what's called the redshift parameter. And that's what our team was trying to measure using SO2 data, is that if this value were 0 or close to 0, or likelihood of this value being 0 is very high, and then the orbit can be explained by purely Keplerian, in Keplerian fashion. If this were close to 1, that means the general relativity it would be the more correct correct method of quantifying the orbit of SO2. So let's see. So this is the bottom line is that our data, at least the SO2, indicates or suggests that Einstein's general relativity model is 43,000 times more likely than the Newtonian model to explain the data. So here is that redshift parameter that I was just talking about, this gamma. So it looks like the best value is around 0.9, maybe 0.85, 0.9 or so. So, and then the Newtonian model is pretty much ruled out in this case, and that general relativity description of gravity seems to really fits well with our observation here. Okay. Let's see. Okay. So, but this is not all over yet. So the Germany group as well, using the Very Large Telescope, did the same experiment. And then we see that our two values are actually quite different from each other. One thing is that the error bars are getting smaller. The data are getting much better these days. And then so this is showing the black hole mass of the galactic center of supermassive black hole and the distance to the galactic center. Right? Those are the two parameters. It's a 17 parameter fit, but the two parameters that we are trying to fit are those two more fundamental values, or the characteristics of black holes. And you see those two values actually differ by more than 3 sigma, so we are trying to understand where this comes from. You know, we are observing exactly same object, data are completely different. We don't overlap much of data at all. So maybe there's instrumental issues every time even the instrument gets upgraded and so on. We have to really understand, or even the adaptive optic gets updated. The data seem to behave slightly different. So we might have to understand all those things. But in any case, this is what we are working on right now currently to understand where this difference comes from. Okay. Oh, I'm going to skip this one. Sorry. Okay, so the future observations. I think I have just enough time to go through this. So what's next? Right? So coming to this, back to this same slide, few slides back, the next one is the precession of periapse. We believe we are pretty successful in detecting the gravitational redshift. So next step is in GR test is a precession of periapse. So, but in order to do that, we have learned that we need to really understand, well, let me go to the next slide, actually. Oops, okay. Let me start this again. Okay, so here's a question. So if all stars move, right? So year after year, you go back to telescope to observe the center of a galaxy. And the picture looks slightly different because all the stars have moved. 2 years later, you go back, all the stars move more, and so on and on and on. So if you think about it, you have a series like 25 pictures that all look slightly different. So how do you tell where's north of that picture, or where west is? As the astronomers really need to know the coordinates, right? And in fact, we are trying to measure the coordinates of every one of those stars extremely accurately to like 40 million arc seconds. So even the telescope is probably not that accurate. Okay, the telescope rotation can be 100th of a degree quite easily, pretty easily. So how do you actually put all these pictures on the same coordinate system so we can actually figure out how these stars are moving? And this turned out to be a little more difficult than we thought, but the first, it's missing the bottom, sorry, bottom here. The first paper was published about 10 years ago, but this is the method that was suggested by Mark Reed at Harvard. And he suggested that he basically came up with the idea of observing masers, those are SIO masers, They are found in the galactic center region. The black hole is right here. SO2 orbit is very tiny, right around the black hole on this scale. But there are 7 masers shown here, and then position those maser stars can be measured extremely accurately using the VLA, the interferometry. Okay. And then so we have basically the position of those 7 stars extremely accurately, assuming the center of the galaxy is at rest. Okay. Every year it's at rest. And then transform the infrared positions to the radio positions, and then you can transform all the stars into this basically the galactic center at rest coordinate system, and then find out the orbits or the stellar positions of all the stars every epoch after epoch. And one of the things we have done is to kind of refine this the reference frame. If you look at the older, I should say, like the reference frame that was used to define those orbits of stars around galactic center back in 2010, almost 10 years ago now, that is this red ellipsis shown. Here is basically delta RA. You can think of horizontal axis and the vertical axis. The center of the galaxy is supposed to be at 0, 0. Okay? But these are the basically position of the center of galaxy defined in that infrared coordinate system that we just defined. And you see 10 years ago, it was not at 0 at all, with a much larger error bars. So now it's come down to pretty close to 0, 0. Within 3 sigma, it is definitely within the center, the 0, 0 center coordinate system. And this is basically velocity or the proper motion of the center of the galaxy that's observed. It should not be observed, it should be 0, 0, but we observe in a coordinate system because it is just not a perfect system that we can recreate. But it's gotten much better to the point that before our GR test, if you look at those 2 orbits of the same star, this is SO2 orbits using the old reference frame coordinate system we had before 2018, and this is a newer one. And you see a big difference where in the old days the orbit did not close. Now, we're not really observing like a precession or anything. It was just artificial thing that came from not being able to put all those many epochs of data on the same coordinate system. Now we are able to. Now you can see this just shows like they line up very beautifully. The data that are 16 years apart sits right on top of each other. Okay, so let's see. So why am I talking about this? Because this is very important for if you want to make any precession measurement, which should be coming up anytime soon. Okay? So the gray line indicates the accuracy of reference frame. There's the stability of the reference frame that needs to be reached in order to observe precession. And we are pretty much over there. So like this year, we should be able to actually start doing this experiment maybe in a year or 2. But I'm still working on this data right now. But by this year, we should reach the reference frame. This is basically how well this reference frame has changed over years. And then we're getting close to be able to make the precession measurements. Okay, 2 minutes left. Oof. Okay. So let me just go over this spin of black hole thing very quickly. I'm no expert on this. So again, if you want to eventually, I mean that's the big wish list, to be able to actually measure the spin of this black hole at the center of a galaxy, again, the resolution is a problem. You want to see stars very close to the central potential, much closer than even SO2. Now, how do you do that? Right now, this is a picture of adaptive optics. So what you use is a laser beam. Laser beam basically shoots up, and it monitors the atmosphere about 90 kilometers above the ground. And so it monitors the atmosphere up there, and then it corrects, undistorts, or corrects the distorted wavefront in real time. But what's problem with this picture is that, getting into details a little bit, but with one laser point or one star that you're monitoring, there's this cone effect that the atmosphere right here and right here are missed. So the new idea is to put more lasers shooting up into the sky, and then so you can actually monitor all the atmosphere above the telescope, right? The 10-meter telescope. You want to be able to monitor what's going on with all the entire atmosphere above the surface of the mirror. And so this is actually an ongoing project at Keck, and then hopefully in a few years we'll have something like this, which means we'll have better picture, we'll have better resolution, and perhaps we'll get one step closer to it. And of course, I only have 20 seconds left, but a 30-meter telescope is the next step, and I'm just going to show this picture, the simulation done by our group. This is the current situation. You know, every time I look at this picture, I thought our picture looked really good. Well, then well, it's not really that great. This is the Keck Plus, the next generation AO that they're working on right now. And you can clearly see the even much better picture that we're hoping to see. And with the 30-meter telescope, TMT, you can see the picture is just, it's what we can get is complete. I mean, just so much better, as you can see. Okay. So I am going to end with this last slide. I did not get to talk anything about the environment of the black hole, but I think this 3D video shows that really well. One of the surprising finding with this black hole study was that there are many young stars near the black hole, supermassive black hole. Now, why is it surprising? Because you don't expect to see young stars around black hole because of tidal force from the black hole. The gas just cannot collapse enough to make stars. But what you see, all the teal colored orbits, those are young stars. And then so you see a bunch of them right here. The black hole is at the center. And another thing you probably saw is that many of those young stars in the disk. Okay? And it shows that a lot of them, those formed at the same time. So there's some sort of pattern to this young star formation. So from orbital studies, because we're able to get orbital data from many of these stars, we can actually pinpoint exactly where they are and how they're moving around the black hole, and are able to, and spectroscopic data will give us the age of the stars. So that was like one really interesting finding that the Galactic Center group found about 10 years ago. But there are many young stars present in this environment. And so we're still studying this. So I know I have to stop now. So I will stop here. Thank you.